Please join me in welcoming to the Distinctive Voices podium, Dr. Cole Soretto.
Good evening, and thank you for having me. I'm very excited to be here, and it is an absolute honor to be able to talk to you a bit about some of my research. So as you can see, I do some research on smoke and wine. This photo here taken in this state, this is a picture from a vineyard in Northern California, I believe. We are starting to get some of this as well in Oregon. And so this is becoming a hot topic, literally and figuratively, for the wine industry. And today I'm going to be talking to you about some of the research that I do and some of the background. When I talk about wine, everybody gets a little excited about discussing some of this because a lot of people enjoy their wine. Not a lot of people enjoy smoky wine. And so this is where I come in, and I'm going to talk a little bit about the chemistry, but I'm hoping to make it very approachable to everyone as well. So for those of you that have had wine, you may not be familiar with some of the characteristics when we talk about smoke-impacted wine. It is not necessarily something that is pleasant for a lot of people, myself included. The sensory characteristics, the senses being aroma and flavor, you'll often have an ashy flavors, medicinal. For me, I often get campfire or rubbery out of these flavors. This can be dependent on the type of fire that you have. For example, Australia has a lot of brush fires, which can impact slightly different chemistries than Oregon with some of their Douglas firs if they catch fire, or here in California with a lot of the grass fires that you might have. There are about 1 in 6 lucky people. I say lucky because I have to drink a lot of these. Having to sip them for some of these sensory experiments, it does become a little bit gross after a while to taste some of these. They linger, they sit in your mouth for a good 2 minutes sometimes, and we are developing rinses in order to allow winemakers the ability to taste their wines relatively quickly, because that is something they do when they are tasting their wines to see what they need to do in order to make their wines as drinkable as possible. And so these flavors, these characteristics could last a long time, and it becomes overpowering. Now, here in California, this is easy to talk about because you guys are very familiar with a lot of the impacts that wildfires can have. I've done this talk, and I know this talk is going to be posted online as well, so I'd like to kind of discuss what it's like going through some of these wildfire events. And 2020 was actually my first year on the West Coast, moving from Florida. Now, I can do a hurricane. That was easy. Coming here on the West Coast, living in Oregon, that was a new experience for me, going through those wildfires. And so as we know from 2020, these wildfires were relatively intense, covering all 3 states on the West Coast. And when the wind changed the following week, it spread across to the other coast. So basically all of our wine regions on the West Coast are being impacted. And in fact, where I'm at in the Willamette Valley, it had the worst air quality in the world for about a week, where all the winds were converging from the California fires, the Washington fires, our own fires in Oregon, and they spread all the way to the other coast. For those of you who have not had the opportunity to experience some of these wildfires, this is what it looked like at my apartment for about 2 weeks. It had that yellow tint to it that is actually the sun you can see here. This is work just outside of the university looking down one of the streets. This is not color edited or anything like that. It is actually yellow. Same thing, this is a picture that was going around the internet around the same time in 2020. This is Salem, about a 30-minute drive north of where I live in Corvallis. And this red color, this post-apocalyptic red color, is the way it looked in the evening, in dusk. And so oftentimes you can tell when you have the prettiest of sunsets and there's a fire way off, they're usually due to fires in the summer. And you do get that red tint and that yellow tint from those. In the United States, when we're talking about fires, fortunately, we are seeing an overall trend of fires decreasing. We are getting better at being able to educate people on how to prevent forest fires and wildfires from occurring. But unfortunately, due to changes in climate, we are seeing that the overall area burned, as you see on the right hand here, is increasing over the years. And so despite our ability to be able to better educate people in preventing the wildfires, the intensity of the fires, the size of the fires, though fewer, are more intense. When we look at other places that are affected by wildfires that have associations with wine, the one that usually comes to mind worldwide is going to be Australia. Australia deals with this almost every year nowadays, and you can see that a lot of these areas that are synonymous with the wine growing regions are also synonymous with many of these regions that have wildfires. And unfortunately, too, these wildfires, as you saw in some of the previous slides, the smoke is not necessarily close by to where you will have the fire, so it can travel long distances. And as I've done some of these talks, this is becoming more of an international thing as well, besides just West Coast United States and Australia. We're starting to see this in Europe as well. We are seeing places that are synonymous with high quality wines, France, Italy, becoming more impacted with wildfires. And some similar statistics is what we're seeing throughout Europe as well. We are seeing that the overall hectares, the area burned, is increasing over time. So we're going to see this incidence of more of those wines that have those campfire characteristics. And oftentimes you may not be able to see this as a consumer, but it is the winemaker, it is the vineyards that are undertaking this economic burden, because oftentimes they do not want to sell a product that they do not want to put out. It does not have those characteristics that they want. So before we start talking about some of the chemistry of the smoke and the chemistry of the wine with smoke, let's talk about wine just a little bit. I think everybody has a good tangible experience with the wine, and I think it's really fun to talk about chemistry and how we as human beings are all chemists. We talk about the sensory experience. That is a chemistry experience. When it comes to wine, most of it's water, a little bit is ethanol, and this kind of everything else is the 3%, and it is this 3%, as this graphic describes, is what brings the magic, as it were. But this magic is just chemistry. It's actually really cool. And it boils down to a handful of chemicals. Now, you don't have to worry about, there's no quiz on this, you don't have to worry about what these are. It's just the fact that they boil down to a few different types of chemicals that are in these wines. From your acids that can give you some of this tart flavor. If you've ever had a wine that has had crystals on the cork, this would be your tartaric acid forming crystals on there. Some of your flavonols, such as quercetin, or your tannins. People often talk about tannins in their wines coming from the skins or the seeds, especially in your red wines. This is the basic chemical of what it looks like. For color and some of the mouthfeel, you can have things like these anthocyanins. So if you ever have a dark purple Pinot Noir, it would be this malvidin-3 glucoside, a type of anthocyanin. One of my favorite chemicals because it is that dark purple color, very intense. And some other chemicals, a little bit simpler compared to some of these other flavonols and tannins, are these monophenols that you see here, guaiacol, syringol, eugenol. These are found in a lot of different plant materials, and wanted to point them out, not in terms of their flavor profile, but the fact that they are there. These are chemicals that we are also seeing that are coming from the wildfires. And so the reason I introduce it here is just to show how complicated this picture gets when we start talking about the chemistry of the smoke. The overall chemistry of the grape changes as we look at the different parts of the grape. If you ever have an opportunity to visit a vineyard when the berries are on the vine, it is often fun to walk around with the winemakers, or if you have a wine chemist handy, you can talk to them as well, they can show you. But they will often show you how to eat the grape and taste the grape so that you can understand the different flavors that are coming out. When you taste a grape and you're walking around in the vineyard, you'll often taste the pulp first, the inside of it. That's where you can get sweetness if it is getting towards ripe, or you can taste very tart if it is still not quite ripe yet. You can get a lot of those tannins, kind of this drying sensation out of the skins, and it will get very dry when you finally bite down on some of those seeds and eventually spit those out. It's very drying because they are chock full of those tannins. Now, what's interesting about wines is the chemistry is varied. And the chemistry is varied in a couple of different ways. When people are talking about wines, sometimes you can hear people say, oh, I get a sense of honey or roses or sometimes bananas. Sometimes you'll hear people talking about dark fruits, light fruits, red fruits coming out of some of these wines. And what's interesting and what's really, really cool about this is that the chemistry is actually the same as many of these other compounds. So when you say something tastes like a banana, you're often getting the same chemical compound that is in a banana. And wine is unique like this in order to kind of have a lot of these other types of sensory characteristics that we don't typically get with other types of beverages and foods, where it has this variety to it. And so when someone says it tastes like bananas, sometimes you may not taste a banana, and that's only because you may not be as sensitive. So there is multiple types of chemistry that's occurring in the wine and for you. Maybe your genetics don't pick up the flavor of, say, raspberry that well. That is me. So if someone says, I get a hint of raspberry in this, I may not taste that because I can't taste that. But I may be able to taste the smoke a little bit better or some of the oak tannins a little bit better. So these experiences that you have are very chemical based, are very personal sometimes, and they're all very oriented in chemistry. So at this point, we're going to go more into the chemistry of the smoke. The chemistry of the smoke really boils down to these three compounds that you see here, these three alcohols. When you're looking at these chemical structures, we're basically looking at carbons on each of the points. Carbons will make 4 bonds, and we assume that if there are no 4 bonds, there are the appropriate number of hydrogens on these points. We are looking at smoke is going to be coniferal alcohol, synapyl alcohol, and p-coumaryl alcohol. These are the compounds that we associate with the aroma and the flavor of smoke. Now in smoke, it is hundreds of compounds that are going into it. CO2, water vapor, ozone. But these are the compounds that are giving you that sensory experience. These compounds are derived from a structure called lignin in plants. Lignin is that very fibrous structure. You don't have to look at this too close. It's a polymer that is made up of those 3 compounds that you saw on the 3 slides. Plants can have a different variation of those 3 types of compounds. And this fiber structure is responsible for the rigidity. So we're going to be seeing this plant a lot, barley. This rigidity in the stem is due to the lignin. For trees, it is the bark. The bark has a high concentration of the lignin in there. And when these decompose during pyrolysis or during a fire event, they're not necessarily forming CO2 going all the way down to their simplest components, but they're forming these aromatic vapors in their singular units that again come back down to these simple monomers that upon that pyrolysis are forming things like guaiacol, syringol, phenols, and cresols. Now I wish it was as easy as these 3 or 4 compounds, but it's not. Sometimes we represent this R group as kind of a group of chemical motifs. In our case, usually a methyl, a hydrogen, or an ethyl. And so we can easily go from 3 or 4 compounds up to 9 to 12 compounds relatively quick. Now, when we're talking about smoke in grapes, we are talking about other types of biology that is interacting. And when we're doing wine chemistry as well, we have multiple types of biology. We are going from smoke, the biology of the plant from which it derived. We're talking about the biology of the grape itself. So when these compounds are in their aromatic vaporous forms, they're in the air, they're attaching to the skin of the grape. This is a relatively hydrophobic molecules that are attaching to the hydrophobic skin of these and absorbing into the grape itself. Now, the grape has its own biology, its own defense, so that it can prevent any damage that these chemicals could cause at higher concentrations. And so we believe there is this natural defense to add these sugars onto these compounds. So here is just a single example looking at guaiacol, adding these sugars, and these are just 2 sugars. There are up to 5 to 7 different types of sugars that can attach to these compounds. So we've gone from 3 to 4 compounds up to close to 30 compounds that we could look for in terms of smoke getting into the wine. And we see this, all of these compounds are elevated in the presence of smoke. But what we do not see is when we try to replicate these experiments, these compounds are not necessarily representative of the sensory impact in wines. For example, if I have an experiment where I have a normal glass of wine that does not have any smoke impact to it, and if I go in and I add each of these chemicals in the same amount as a smoke impacted wine, and I have people try it, they will not taste the smoke. They might taste something that is chemical kind of tasting, but not necessarily smoke impacted. So this is where we come in. We're trying to figure out, we know that the smoke is imparting these compounds, but there's no good sensory experience to tell us what the chemical compounds are. And if we know these chemical compounds, are we able to better target them so that we can pull those chemicals out during the winemaking process so that we can help people have good wines and help winemakers make the wines that they want? So again, our aim is to identify those unknown compounds that are imparting those flavors and able to better identify them, and for chemical avenues of amelioration. How can we find it out? How can we take those compounds out for the winemakers? So we came up with a scheme. How can we track the chemical compounds that are going into the wine from the smoke? So the first thing that we want to do is be able to track our smoke. So we're not even at the wine stage yet. We are making a smoke source. In our case, it is going to be barley, which I'm going to describe here on the following slides. So we take something called carbon-13 CO2 that I will describe also in further slides, introduce it into our smoke source, in this case barley. It is going to get absorbed into the barley and eventually get absorbed into that lignin we had talked about earlier. Upon pyrolysis, a fire, these compounds, the carbon-13 as opposed to carbon-12, we're going to have a lot more carbon-13 in our smoke than normal. So our smoke will have these labeled pieces of carbon and these volatile organic compounds. We will expose this smoke to our grapes, make the wine, and do our chemical analysis. And I kind of breezed through this section, but honestly, this is probably one of the longest sections we're doing right now. And so this brings me to the work that we had done. I moved to Oregon in 2020 after I graduated with my PhD at University of South Florida in Tampa. And so I went from a chemical lab doing research, doing spectrophotometry, doing NMR, and very quickly in 2020, things were shut down. But I was fortunate enough, and my sanity was honestly saved because I had the opportunity to work in a greenhouse for almost all of COVID, And so this was an absolutely amazing experience. I got to go into work every day, work by myself in the greenhouse, get out of my apartment, growing this barley. And we had several batches going at a time. We chose barley in our case as our fuel source for this smoke for several reasons. The chief of which is because it has rapid growth. I can grow a bunch very quickly. I have 4 concurrent batches, I think I counted earlier today in this slide, going at the same time. It takes about 10 weeks, and I can rotate these every so often. We also have local expertise. We have a professor, Pat Hayes, and his group that work on barley itself, and that is where we got our original seeds for the barley. And it's great growth for year-round. So I can do this in the winter, I can do this in the summer, I can do this when there are COVID lockdowns. So the carbon-13 that we're doing is slightly different than the carbon that we typically get. Normally, we have carbon-12, meaning you have an atomic mass of 12, 6 protons, 6 neutrons. Carbon-13, on the other hand, has that extra neutron. So in our case, 6 protons, 7 neutrons, and for something like guaiacol, the mass will change from a total of 124 up to 125 to 131, depending on how evenly distributed the carbon-13 is in these compounds. There's a few benefits to this. The natural abundance of carbon-13 in the air is about 1.1%. In plants, it is about 1.08%. Plants are selective against carbon-13. So this gives us an opportunity to understand with even more confidence that higher elevations of carbon-13 come from our smoke. And we have a variety of instrumentations that we can use in order to measure this as well that are targeted towards carbon-13 and that is far safer from some of the radio-labeled compounds. So once the barley was grown to a certain height, there is a growth phase which it starts to spring into a faster biomass accumulation. We place them in these cages that we had developed here, basically just PVC and a ton of duct tape. We had carbon CO2 meters inside these, and we had these small tanks with carbon-13 CO2 in these tanks, where we basically did something called pulse labeling. We purged out all of our CO2 down to less than 50 ppm of the natural CO2, carbon-12 CO2, and pumped in about 2,000 ppm of carbon-13. So for reference, natural carbon in the air, CO2, is about 400 ppm present day. Here, we're pumping in about 2,000 ppm. We want to force the plant to take up the carbon-13 and give it no choice but to take that up. So we leave these in these incubators for about 5 days, and we learned very quickly that this is basically a secondary greenhouse. So we had to air these things out in order not to kill these plants. We wanted to be able to use them in the future. So we would let them air out over the weekend, and then on Monday, come back in and re-sleeve them and do another 5 days worth of pumping CO2 into these containers. After that, 10 total days inside these containers, we let them dry out to about constant weight. Generally, we can let them sit in the greenhouse. It's very dry, it's very warm in there year-round. It's absolutely wonderful in the Pacific Northwest when it's winter and raining and just very dreary out to go into the greenhouse and just hang out there for a while where it's nice and warm and you can see the rain outside. So it stays relatively warm in there, and we can allow the barley to dry out in there. The proof of our success is in doing something called isotope ratio mass spectrometry, looking at the abundance of carbon-13. So if we look at our untreated samples, they were basically exactly what we'd expect, about 1.07 to 1.08% of carbon-13 under our controls, things that never saw our elevated carbon-13. When we look at our partitions here, we are seeing anywhere from about 4% up to about 10% in a few trials. So what we had done is we wanted to see if there is carbon-13 evenly distributed in the plant, or is there some sort of partitioning where it is going to some of the newer material versus the old material. There is a relative trend where we are seeing that there are elevated amounts in some of the newest material, say leaf 4 being some of the newest material versus some of the oldest material being down towards the rootstock. But overall, we see a relatively no statistical difference between our leaves, 0 and leaf 4, and same with our stems from stem 1 up to the newest material at stem 4, giving us the conclusion that, number 1, we have elevated carbon-13 at almost 10 times the amount in certain cases, and we don't have to worry about partitioning these even further. So we can use our whole stock of barley in this case, and it will achieve the elevated amount of carbon-13 in our smoke when we burn this. So at this point, we have talked about getting the carbon into our plant. We now have it in our C13 lignin and all in our barley. The next phase of this is going through the burning process, creating this carbon-13 monomers, the guaiacol, the syringols, this carbon-labeled smoke, and introducing it to the grapes. This is what we did in 2020, September. Post-harvest is a proof of concept up front. We did this. Oregon is very well known for its Pinot Noir and Chardonnay, so we are funded partially by Oregon funding agencies, so we are specifically looking at the Pinot Noir and Chardonnay. I know Anita Oberholster at UC Davis. She often looks at more of the Napa Valley Cabernets, that sort of thing. But for our case, looking at these two in a post-harvest experiment, we hung up a whole bunch of grapes and basically piped smoke over using about 5 grams of our dried out barley measuring the amount of smoke. Now, the smoke in these is really high. We do this about 6 hours a day for 3 days, and we do it on different trials. We have 3 trials, 1 trial per day, 6 hours per day. And we basically sit out there. It's usually nice around this time of year, maybe a little chilly towards the end, but we get to sit outside, hang out, and pump in a lot of smoke. The smoke that we're pumping in is that carbon-labeled C13 smoke. The AQI scale, which I assume a lot of people in California are very familiar with, that I got familiar with my first year in Oregon, it kind of breaks at 500. After 500, the math no longer works. For us, the math no longer works. I can't use the AQI scale. That's how intense the smoke was that we were getting inside these cages. The AQI scale breaks at around 500 micrograms per cubic meter. We were up near 100 milligrams per cubic meter. It was a ton of smoke that we were pumping in there. We wanted to not guess as to what chemicals are going into these grapes. In our second year, we scaled this up. We took this out to a pre-harvest. We went to the vineyard. We have our own vineyard at Oregon State University that is out in Monroe called Woodhall. And we were able to design these cages just in a very large scale up where we could encompass 3 vines at a time of both the Pinot Noir and the Chardonnay again, encompass them and pipe in some more smoke. Not nearly as much concentration of smoke given the size of these cages, but we were able to achieve, again, breaking the AQI scale, achieving very high smoke densities between 20 and 40 milligrams per cubic meter in these tents here. And you can see there's a lot of design challenges when it comes to this, something that I never thought I would be doing when I was sitting at a bench in my grad school career, working in a vineyard, designing cages from the inside and the out, and piping smoke into these cages. There's a lot of fans in here, there's a lot of smoke meters, there's ways of improving this. As you can see in our final year of doing this, what we had initially saw in 2021 is that this can stress out the plants. The method that we are using can really stress out the plants. So we wanted a way that didn't necessarily add heat stress to our vines. One of our colleagues tried our method and his got so hot it basically cooked his vine. So we wanted to try out a new experiment. Our vines were fine, our experiment went well, but tried slightly different experiments with the shade cloth, and this worked much better. We were able to preserve the health of the vine with the exception of all the smoke that we pumped in there. So now we know that the stressors from 2022 is basically due to the smoke and not necessarily due to high heat or high humidity. And again, we are pumping a lot of smoke in here, 20 to 50 milligrams in our third year, using 10 grams of our barley that we had been growing now for the third year at this point. And so we did this each day, same thing as the first year, did it over the course of 3 to 4 days. We did this for 6 hours. Again, relatively nice days out there, sitting out in the vineyard, watching the turkeys run by and the squirrels try to take off with your lunch. And we eventually make our wines. The wines that we make for this, we don't necessarily need to make a good wine because we're just testing it for the carbon-13 and what happens. So we don't do a lot of aging in barrels. We don't want to complicate the process too much, but we do go through the fermentation process that we would go through for Chardonnay, for Pinot Noir, in order to have a relatively normal wine, although they do taste very, very smoky. The way that we have to transfer our wines is often using mouth siphon. In my first year, I was not very well seasoned at this, so I had my fair share of drinking mouth siphoned wines during this process. So let's talk about the data, finally. Proof of concept, like did it work? So when we look for our carbon-13 compounds, we can start with some of the things that we know about. Again, we're looking for some unknowns, but we need to make sure that we understand that this worked first. So we look for something like cresol. Cresol was one of those chemical compounds that we had seen in the past. So if it worked, we should see something that weighs about +7 from 108, which is about 115. So proof of concept, we can actually see that this carbon-13 using GCMS in this case, gas chromatography mass spectrometry, here we're measuring the masses of things. We are seeing that when we check this against our internal standards, we are seeing this cresol come out with a weight of more than 7 plus 7 of what it previously was. So proof of concept, we're showing that, yeah, we got some of this smoke in some of these grapes. Same thing with guaiacol. Guaiacol, a little bit more challenging for us. We're still trying to piece out some of the data on this one, not necessarily as distributed. We're not sure if this is because the biochemistry of the guaiacol is slightly different than that of the cresol, or if maybe it's just the data processing is not as clear as it is for the cresol, but we're still working on it. But we are seeing proof that the guaiacol does weigh more. Therefore, we have some of our smoke, the carbon-13 labeled smoke, getting into our wines. But we weren't necessarily doing this for proof of concept. We're looking for new chemical compounds. The new chemical compounds, now this is where the story gets a little bit muddy. It's not that I necessarily found these compounds, but we've been working in conjunction with many other collaborators. And initially, this contribution was by another collaborator, Tom Collins at WSU, Washington State University, started getting clued in. I'm going to tell you the rest of this story kind of like in a haphazard way. But he clued us in on some of these chemical compounds that we had started detecting due to another sensory profile that we had done looking for ashy standards. And what we were able to find is a compound that looks incredibly similar to what we saw on the last slide. So on the previous slide, we were looking at a cresol, but that cresol had an oxygen in this corner over here. And in this case, we see a carbon-13 labeled thiocresol with a sulfur in the corner. So this is telling us that sulfur is getting into some of these chemical compounds. Now, we know that the smoke doesn't necessarily have these thiols in them. There's been many studies over the years. There's not any indication that these thiols are in the smoke themselves. So this leads us to believe that there is some sort of biology, some biochemistry that is occurring either during the winemaking process or in the grape growing process that is changing, potentially, some of these OHs, the oxygen, into this sulfur. And we know that it is coming from our smoke because we are seeing this with the carbon-labeled ring here. We can see this similarly for the thiol version of the guaiacol, whereas this would typically weigh 140, but the carbon-labeled version, we are seeing a weight of 147 on this. But this is just new compounds. Sometimes the chemistry doesn't necessarily tell us the way something tastes or if there is flavor. And so with this in mind, we actually did a little bit more chemistry to this. This is just repeating kind of what I was just saying. We've seen many of these compounds now. We are assuming at this stage that as it goes from coniferal alcohol to guaiacol into this thioguaiacol that you see here, or the thiosyringol, or a benzene thiol from a lot of these. And we are suspecting, for anybody that has done any sort of sulfur chemistry, that there is a lot more out there. But again, this doesn't necessarily tell us about the sensory experience. The sensory experience, this is where the theory, the chemistry of it meets the perception of it. So if you were to have a wine with the thiols in them, does it taste smoky? And so this is what Dr. Tomasino and Jenna Fryer had submitted. And what they had found is that if you take they did a Syrah and a Grenache in this case from Washington State that had basically no smoke, is what they're indicating by low here. The P indicating phenols. Now, if you add the phenols in this case, it corresponds to this graph in relatively the same region. So if you look at the Syrah with just phenols, it comes off as kind of a chemically flavor. This one's kind of challenging to talk about. If you ever walk into, maybe not a nail salon, but you kind of get that very chemically sort of aroma coming out of something, that would be that kind of chemically. When you have just the thiols, you can get some of this vegetal, maybe perhaps ashy. For me, it kind of comes off a little bit more rubbery. But we don't necessarily get the smoke still when you add the thiols in the amounts that we were detecting them. So interestingly, it's not until we mix those phenols, the guaiacol, the syringol, the eugenol, with those thiols the thioguaiacol, the thiosyringol, that you start achieving, again, these corresponding to their relative regions, ashy, smoky, and even more rubbery flavors and aromas in some of these wines. So the conclusions that we can make out of this is that those phenols, those guaiacols, do not alone impart those chemical flavors, or impart the chemical flavors, but not necessarily the smoky flavors, confirming everything that a lot of the researchers had been saying before. And again, the thiols are also not imparting that flavor as well, kind of coming off as a rubbery flavor, but it's that combination of the phenols and these benzene thiols that are actually giving us this experience of the smoke campfire-y wine. And this is actually the experiment that kind of got us started. It was this and an ashy standard. So when we're doing sensory experiments, we're often talking about standards. If you want someone to be able to understand what, say, raspberry tastes like, you hand them a standard and then have them describe what might taste like a raspberry. For us, for chemicals, we were looking for an ashy standard. The ashy standard that we had come up with from Dr. Tomasino and grad student Jenna Fryer was that burnt leaks was our standard. And it was during that process that we had started doing some of the chemical analysis of those burnt leaks. And that is where Tom came back to us and said, guys, the burnt leaks have a lot of thiols in them. Compared that to the wines that were smoke impacted and saw those thiols. And I was able to confirm it on those previous slides that you saw there. Things that we're currently working on right now, there are a lot of things that we are working on now that we have a little bit more sense of what the chemistry is of some of this smoke. I will say that there is still more chemistry that is occurring that we are still investigating. We're still trying to prove what some of these compounds are beyond a reasonable doubt. We are looking at ways to prevent the smoke from getting absorbed into the grapes. One group that we are collaborating with at OSU, Trung Tran, is working on coatings in order to prevent the smoke from getting in without impacting the quality of the grapes, and he has showed some success. I mentioned earlier where the winemakers will taste wines, giving them an ability to reduce something called carryover. Carryover is that point when you taste one wine and you go to taste the next wine and you still taste the previous wine. So in this case, she developed a way, Jenna and Dr. Tomasino, to reduce the carryover down to about 60 seconds or so for some of the smoke just by using a pectin rinse. And then finally, another thing that we're doing, and this is gonna be ongoing, I know for us in Oregon, it is our group that is looking at some of the background chemistry. So I'd mentioned the guaiacols, the syringols. Those are all inherent in almost all plants. They are there because there is that conversation of biochemistry in the plants. But a lot of winemakers and a lot of grape growers don't know how much of those compounds are in their grapes naturally. So if they give us a sample and say, can you tell me if it's smoke impacted? We can't really tell them if it's smoke impacted. We can just give them numbers. And if they don't have a number to reference it to, then they don't necessarily know how to make informed decisions. So currently we're working on the background chemistry of the smoke compounds or smoke-related compounds such as the guaiacols in grapes all across Oregon. And I think there are researchers doing this across Washington and California as well. I will end it here, and I will thank my group. I will thank all of you and thank all of our funding from USDA and Northwest Center for Small Fruits. And I will hand it back over to Jennifer.